like just adults on Instagram. They can just do stuff like this all the time. They just like bench. Like,
Yeah. It's my last class of the day. Huh?
let's go.
Yeah.
Yeah.
I feel like tomorrow they should put fifth last.
Yeah, because it's a lunch period.
Yeah, the lunch period should be the last period, so that one of the days you have like.
I don't have to roll. I don't fall asleep like 10:30.
I guess that's also nice. You come up later.
Yeah, I don't have to be so for real.
Wait, is it different?
No, I think that's the same as today's.
Okay, so I still should be here.
All my homies take spreads. I wouldn't fall enough.
I think so, yeah.
Yeah, I don't like the breakdown of these top break days because I have 2 classes to get today. And actually, I really just have this class today. Because I have soccer and then Latin, and we didn't even have a Zoom today. I just sat in the chat board, then this and then lunch. And then I have 4 classes tomorrow. I should have. Actually, I should have just stayed home.
Should have just went home.
Well, I mean, I didn't show up until 10:10.
Did you guys have soccer this morning? Oh, you didn't because
No,
they were
it's-
signing.
Our season's over. Jess is still soccer, but all the seniors are done.
Oh,
I still have soccer.
Yeah, 3 with you.
What does it have?
that you're not a senior?
You still technically have soccer.
Yes, but the seniors don't go. What's your 3v2?
Bro. They haven't lost it.
Dang, progress team.
Kind of cried. We beat them.
And I'm like, oh, this is terrible.
All right, guys, you have a problem set due end of the day tomorrow from last week's lessons. The first 2 lessons from this week are on the next problem set due Tuesday of next week. And then today's and Mondays will be on the next one. And then I guess it's maybe Tuesday and Wednesdays will be the very last problem set. So each problem set's only got 2 sections on it for the rest after this one that's due tomorrow. I have only 2 sections each, and then we're done. So today we are doing lesson 32 out of 35. Which is really close to finishing. This is one of my favorites. I like the cryptography one. I think it's kind of cool the way it works. So we're going to talk a little bit about cryptography, modular arithmetic, which is something that people in computer science have said they've seen modular arithmetic. Most people have not seen it in any of their high school math classes. You would see it in quite a few college math classes if you continued to take any math classes in college. You would see modular arithmetic, and it's part of what we'll do in cryptography. So all we mean by cryptography is encoding and decoding of information. This is a huge deal in today's world because all of our information needs to be encoded and decoded because people are constantly hacking at your personal information, your financial information, all that stuff. The ciphers that we look at today will be very simple, not good ones to use for really sensitive personal information, but they are pretty hard to decode if you don't know it. If you're not like a professional hacker, you're not probably going to be able to figure out even these simple ones that we're doing. They worked really well before the advent of the computer because, or at least the modern, like really powerful computers that can just do billions of calculations in a very short amount of time they can kind of hammer their way through these types of ciphers just through force. But otherwise, there's not a mathematical way that's very easy to break even the ciphers we're going to look at today. So most of your like bank information, all that stuff, way more complex than what we're looking at, the way that they would encode that information. Okay, ciphers are just algorithms for encoding and decoding information. We're going to be using matrices for our ciphers. It's not the only ciphers that exist. There's all sorts of things you could use. First, we're going to have to look at modular arithmetic, which is just using a system of integers where numbers wrap back around on themselves after reaching a certain value. The reason we have to do this is if you use a matrix to encode, the English language 0 through 25 numbers representing letters, you don't want to get numbers like, numbers like 200 back or whatever. Why is it coming back? There we go. You don't want to get numbers like 200 back. If I encode letters 0 through 25, I want to get 0 through 25 back. When I'm decoding, I don't want to get all these big numbers. And when we multiply by matrices, there's no way to guarantee that other than using modular arithmetic. So what we'll get is basically the way we keep those numbers wrapping back around on themselves. They're the remainder after you divide by this letter, this number P that we'll specify. So for example, if I'm in modular 5, I would have the numbers 0, 1, 2, 3, and 4, and that is all. No other numbers would exist. Once I got to 5, the remainder of 5 divided by 5 is 0. 6, the remainder is 1. 7, the remainder is 2. 8, the remainder is 3. 9, the remainder is 4. Then 10, back to 0, because the remainder divided by 5 is 0. So it's basically taking the remainders of the numbers, and those would be our integer values that we have in that system. No negatives, no fractions, no decimals, no irrational numbers. Literally, these are the only numbers that would exist. And so as we add, subtract, multiply, and divide, we would continually take remainders when dividing by 5 of those numbers. So like 3 times 4 is 12. 12 doesn't exist. So we'd say, what's the remainder when I divide 12 by 5? It's 2. So 12 would be 2 in here. Okay, so we use the congruent symbol, but not the geometric congruent symbol. This is the modular congruent symbol. It's just 3 bars. Equal sign with an extra bar, because it's otherwise it would look weird to be like 16 equals 1. 16 is congruent to 1 mod 5. So this is how I would usually write something. If I get some number that's not in my mod 5 system, I would say 16 is congruent to 1. So basically, as I use 16 in mod 5, it behaves like the number 1. Okay, you can get to that again, either divide 16 by 5, that goes in 3 times, you get 15, you subtract, and there's your remainder 1, which is pretty convenient for small numbers. Once they get very large, it's not a very great way to do it. With calculators, it's a lot easier. You also can essentially do division by a series of subtractions. Right? If we have 16, we could get to the remainder by just subtracting 5 or multiples of 5. 5 behaves like 1 in mod, like 0 in mod 5. So I can literally add or subtract 5 as many times as I want. I should get something congruent. So I could just keep subtracting 5. And that's the remainder I'm getting when I divide, right? That's my 3 5s that went into 16. And then my remainder of 1 is what's left. So with large numbers, a lot of times if I have like 243 mod 9, and I don't, or mod, let's do even larger, mod 15, and I'm trying to figure out how many times 15 goes into 243, and I don't really want to do long division, I subtract a large multiple of 15 to bring 243 to a much smaller number. And that's like subtracting 0. It doesn't really do anything other than make the numbers small and easy to deal with. The other place this is really useful is when I do negative numbers, I don't ever do division. It's like if I had -7 mod 5, add a multiple of 5 until you get a number 0, 1, 2, 3, or 4. Okay, otherwise you'll have a remainder of -2. If you try and do division here, you'll have a remainder of -2, which you'd still have to kind of deal with, which is still 3 mod 5. So I usually, especially with negatives, add 5 until you get to a positive number between 0 and 5. 0 included, 5 not included. Okay, so we'll do some practice with this. So when I see y is congruent to x mod p, so like 16 is congruent to 1 mod 5 is what we just said. It's equivalent to saying y is something times p plus x. So like for us, 16 is equal to some integer times 5 plus 1. Q is not important for us. We kind of throw that one out. But all it means is that 16 should be a integer multiple of 5 plus 1. X goes from 0 to p minus 1. Yeah. Okay, also this means that y minus x should be divisible by p. So for us, 16 minus 1 divided by p, which is 5, should give me an integer. So those are all kind of equivalent statements here to when we say y is congruent to x mod p, y minus x should be divisible by p, y should be some multiple of p, p plus x. Okay, but we'll pretty exclusively use this notation here, but they mean the same thing. Okay, when I'm adding or subtracting, if my numbers get larger than p, I do mod p again. So say I have 13 and 26, and I want to add them together mod 3. You can either add 13 and 26, right, is 39, which is divisible by 3, which means the remainder will be 0. Or you could mod 13 and mod 26 and add those numbers together. You should get the same thing, whether I add them, then mod them, then add them. This is 3, but 3 is 0, mod 3, right? There is no remainder of 0 when I do mod 3. So 13 plus 26 is 39, remainder of 0. Or I could do 13 will have a remainder of 1, 26 will have a remainder of 2. Add those together, I get 3, that remainder will be 0. So you can, I kind of like this method, modding it first. It keeps the number small and easy to deal with. That if I have these really large numbers and then I add them and get even larger numbers, and then I have to deal with remainders, for me, it's easier as I go along to just keep them small a lot of the time. Same with multiplication. I could do 5 times 7, which is 35. Okay, when I mod 35, mod 4, right, I'll get the closest, I usually in my head, I think the closest multiple of 4 is 32 to 35. So I would just subtract, and that's going to be 3. But it's the same as 1 times 3. If I modded 5 and got 1, modded 4 and got 3, multiply, that's 3 mod 4, which is the same as if I did 35 divided by 4. I would have a remainder of 3 because it would be 32. It was, the closest 4 would get to 35. So you can mod, then multiply, multiply, then mod, doesn't really matter. Okay, the hardest part for most people in this section is there is no division in modular arithmetic. So no fractions, no division, no decimals. but there are still multiplicative inverses, which just means something I can multiply to get 1. Right, so when I'm solving an algebra 1 problem, like 3x equals 5, and I'm trying to figure out what is x. Yes, we divide by 3 on both sides of the equation a lot. Instead of dividing, think, what can I multiply 3 by to get 1? That's what we mean by multiplicative inverse. Right, multiply by 1/3, we always say cancel. Really, that's giving you 1. It tells you what 1x is, 5/3. Okay, so in normal kind of algebra 1, we could solve all using multiplication, no division. Here we have to do that. We won't have any division. So instead we have to think, what would I multiply by to get 1 in this modular system? So if we have some number n, we're trying to figure out what do I multiply n by that when I divide by p, I have a remainder of 1. So this is the most kind of complicated thing, in my opinion, of today's notes, is this idea of a multiplicative inverse. We cannot divide, and we have no fractions. So we're trying to think, what would I multiply by that then would give me a remainder of 1 in this modular system? That is a multiplicative inverse. Okay, so for example, inverse of 3 mod 11. So our choices are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Those are the only numbers that exist. Okay, no fractions, no decimals, no anything else, no division. We can add, we can multiply, no division. So multiplicative inverse of 3. You're trying to think, or at least the way I think about it, what would I multiply 3 by to get something that is 1 more than a multiple of 11? Okay, that way when I divide, I will have a 1 remainder. So like 3 times 0 is 0. That's just 0. 3 times 1 is 3, which is just 3. 3 times 3 is 9, which is just 9. 3 times 4 is 12. 12 is 1 more than a multiple of 11. That's my inverse. 3 times 4 is 12, which if I divide by 11 has a remainder of 1. 3 and 4 are multiplicative inverses in mod 11. Meaning if I have a problem and I'm trying to kind of eliminate a 4, I multiply by 3. Not by a fourth, not divide by 4, you would multiply by 3. And that would kind of cancel out 4 because you'd get 12, which is 1. And then you could solve a problem. Okay, so if we had an algebra problem we're doing with mod 11, to eliminate a 3, I would multiply by 4. Okay, 7, you could basically do the same thing. The larger p gets, the more this is kind of just a lot of arithmetic to be thinking through. But I'm trying to think of a multiple of 7 that's 1 more than a multiple of 11. So like 7 times 2, 14. 3 is 21. Still not 1 more than a multiple of 11. 4 is 28. 5 is 35. 6 is 42. 7 is 49. 8 is 56. Which, if you're good with your multiples of 11, hopefully you think 56. That's 1 more than a multiple of 11, right? If I divided by 11, I would get 1 as my remainder. Which means 7 and 8 are inverses. So again, if I wanted to kind of eliminate a 7, I would multiply by 8. If I was solving like a basic algebra problem in a modular 11 system. Okay, not every number will have an inverse for every p. So think like 2 mod 4. There is no inverse. There's no multiple of 2 that's 1 more than a multiple of 4. Every multiple of 2 will either be a multiple of 4 or be 2 more than a multiple of 4. But you'll never get a multiple of 2 to be 1 more than a multiple of 4. Same with 10 and 25, right? I could get multiples of 10 to be like within 5, of a multiple of 25. But I'm not going to be able to get within 1, right? No multiple of 10 is 1 more than a multiple of 25. 7 and 21, same issue. Okay, I could get within 7, I could get within 14, I could get with to be an actual multiple of 21 and get a remainder of 0, but I'm not going to get a remainder of 1 with any multiple of 7. So as a general rule, n will not have an inverse in a mod p system if n and p have common factors other than 1. It's like all these examples, like number 1 here, they both have a common factor 2. Number 2, they both have a common factor 5. Number 3, they both have a common factor 7. That's what's stopping us from being able to get within 1 unit of the p value when I do those multiples. So if they have common factors, there will be no inverse. These will be things we need to avoid in terms of cryptography. We need an inverse because it doesn't matter when we're coding, but when we're decoding information, you cannot decode if there is no inverse. That's part of the decoding process, in which case you've coded information that can never be brought back. Okay, so we need there to be an inverse in order to decode our information. So for that reason, p being prime is often really useful for our ciphers because every n will have an inverse if p is prime. So we often use p equals 26. Like a lot of our examples will use p equals 26 because there's 26 letters. So we can just assign every letter to a number and we use 26. What you then need to watch out for is determinants that are multiples of 2, any even number, or multiples of 13. Okay, as long as we avoid those, p equals 26 is fine. But it's probably not very hard to get to 29 or some prime value by adding some symbols, add a period, add a space, add a question mark, whatever, and assign those numbers as well. And then not only do you have some punctuation, so it's easier to read your message, you're at a prime value, you don't have to worry about the determinant. But yeah, a lot of our examples will use 26. And therefore you probably could use, you might have homework problems that were like, why would this be a bad cipher? Odds are it's because your determinant and your p have a common factor. Okay, that's usually why a cipher would be a bad choice, because then again, there's no way to decipher your information. So the Hill cipher was published in 1929. Very hard to decipher at that point, because again, without a pretty powerful computer, it's hard to just kind of brute force your way through figuring out the Hill cipher without having the cipher itself. Up to that time, people encoded things by just kind of mixing up the alphabet. So it'd be much simpler algorithms, which is something I feel like people do when they're little kids. You can send secret messages by just saying, well, everywhere you see an A, it's really an M, and everywhere you see a B, it's really a P, and everywhere you see a C, it's really an X, or whatever. And you just kind of assign letters to other letters, write this jumbled message. The person on the other end has the same ones, they can decode it. You get a lot of worksheets that have this. We had one in BC in the related rate section where you're like, solve a problem, you get a number, and then that's a letter, and then you go fill in this message that you've decoded. It's just jumbling up the alphabet. This is really easy to decode even without a computer. Okay, if you have a long enough message or several messages, you just start to look for patterns that you're aware of in that language. Like in the English language, I'd start seeing double letters. And I know certain words, certain letters that make sense to put next to each other in English. And so you could start to narrow down what do those numbers probably stand for. Or I see a letter by itself. And I'm like, well, there's only certain letters that really make sense to put by themselves in English or whatever. So you'd start to find patterns. You can start to look, I don't know, remember what they are, but there's like probability. You can use that to figure out like, there should be a lot of E's and certain letters that occur very frequently in a English sentence. You could start to figure out stuff like that as well. So you could really start to decode these things even without a computer, just with lots of of statements, you could kind of start to figure out what things are until you got something that made sense. The Hill cipher doesn't keep any of those patterns. So it completely scrambles the word. So what was an E will not always become the same other letter once it's scrambled. It completely scrambles it. So double letters do not become double letters in the Hill cipher. An E here may have become an X, but the next E may have become a P. And so there's no way to kind of see, oh, there's lots of these letters. That's probably a common letter like an E or an R or an S or a T or whatever. That doesn't happen either. So the Hill cipher is really hard to decipher without having the original key. Again, unless you have a computer that can just do billions of things very quickly and just kind of like hammer through and see if it can figure it out. All right. So we use modular arithmetic and matrices to encode and decode. You can choose any P you want. Again, P equals 26 is common in a lot of our examples. Choosing a prime is convenient because then you don't have to worry about accidentally choosing something that can't be deciphered. Because we'll need an inverse in mod P to decode. That's how you decode, is you have a matrix that encodes, the inverse of that matrix will decode. And you can't get an inverse if you can't get the inverse of the determinant. Okay, so you could get other P's than 26, again, using symbols or whatever. So if we use A mod P to encode, A mod P just means all of the elements in A are from modular 26, or modular P, sorry, not 26, P. So meaning every element in A is an integer from 0 to P minus 1. We'll need the inverse to decode. And the inverse only exists if the determinant of the inverse exists. Because remember, when we're finding the inverse of A, we usually divide by the determinant and then do some other stuff. Well, here we have, again, there is no division. We don't have fractions. So instead, we'll multiply by the inverse, inverse of the determinant of A here. Meaning we need to have an inverse for our determinant. So if you're using mod 26 and your determinant is 20, you won't be able to decode the message since they share a common factor of 2. Okay, but if your inverse is 21 and you use mod 26, no problem. Okay, they don't share a factor. There will be an inverse. You can invert it, you can decode it. So the only thing you'd really have to worry about is if you use 26, the determinant of A should not be divisible by 2 or 13. Or else you won't be able to decipher. So we have to make sure that the determinant's inverse exists, because that's the division step we normally do, is we're going to actually multiply by the inverse instead of dividing by something. Okay, so how do we decode a message? We find the inverse of A, whatever we use to encode. You can use Gauss-Jordan or cofactors, same as we've done in the past. It's just that you stay in the mod system. So meaning, again, no fractions, no decimals, no negative numbers, no division. So as you do Gauss-Jordan or cofactor methods, you would, anywhere you wanted to divide, you would actually multiply by the multiplicative inverse instead in that mod system. Anywhere you added or multiplied and got something outside of that system, you would remod. So if I was in mod 4 and I got a 6, I would change it to a 2. And you just stay in that system. Otherwise, they're the same. So we'll do some examples of how you find the inverse. The two main ways we've learned. Probably, well, not probably, definitely on your test, you will have a 2x2 doing this. Because again, already a 3x3 is pretty arithmetic heavy to invert. To then have to be doing mod whatever the whole time, it's tediously lots of arithmetic. It's not that it's difficult. You should be able to do it. It's multiplying and adding. but it is something that takes a while. It's a lot of arithmetic. It's easy to make mistakes. So I'm going to stick to 2x2s on the test, but you should be able to see how you could do other things. So we're going to find the inverse of 2021 mod 3. So I'm going to use Gauss-Jordan first. So we do 2021 and just put that next to the identity 1001. Okay, I'm going to eliminate the 2 in the second row first, just like we normally would. I'm just going to subtract 2 times row 1. And so I'll have 2, 0, 1, 0 will be my first row. 2 minus 2 is 0, 1 minus 0 is 1. 0 minus 1 is -1, would be here.
Wait, I thought you said you couldn't subtract though.
You can subtract, you can't divide. Yeah, yeah.
Oh,
Sorry, yes, -1 row 1. Sorry, thank you. Because it's already a 2. So 2 minus 2 is 0, 1 minus 0 is 0. 0 minus 1 is a -1. That's not in modular 3. We should have integers from 0, 1, and 2. So we would just kind of remod that thing every time as we're going. -1 is 2, mod 3. Okay, basically, I add 3 until I'm between 0, 1, and 2. And then 1 minus 0 is 1. Okay, now I want to kind of deal with this 2, the first element in the matrix, and I want it to become a 1. We normally would divide by 2 or multiply by a half. Those two things are not possible. We need to multiply by the inverse of 2 in mod 3. Mod 3 is easy because there's not a lot of choices. Either I do 2 times 0, which is not 1, 2 times 1, which is not 1, or 2 times 2. 2 times 2 is 4. The remainder when I divide by 3 will be 1. So I'm going to multiply this whole row by 2. 2 times 2 is 4. Mod 3 is 1. 2 times 0 is 2. 2 times 1 is 2. 2 times 0 is 0. Okay, and so we have our identity on the left. So we have the inverse on the right. Notice they're inverses of itself. In this case, not always. So 2021 is the inverse of 2021 mod 3. Okay, and you could check your work, multiply them together. 2021 times 2021 is going to give me 4, 0, 6, 1. Which in mod 3 is 1, 0. The remainder of 6 is 0, 1. So it does give me the identity in mod 6, right? The remainder of 4 will be 1. The remainder of 6 will be 0. So that's just 1, 0, 0, 1. So with the 2 by 2, this should not be terribly difficult, other than you need to make sure you know things like you're multiplying by inverses rather than dividing. That's the only step that really changes much. And then every time you get something like a -1 or a 4, you have to kind of I guess you can't really get a 5. In mod 3, there are not a lot of options. But if the number was bigger there, if anything's outside of 0 to p minus 1, you just remod to get back where you belong. Okay, cofactors for 2 by 2s, that's our shortcut. For anything larger, that's where we did the cofactor method. So here we would find the determinant. Determinant is 2 minus 0. Just make sure you mod it if it wasn't already. So 2 is fine to have, but if I got like 4, that's going to be actually a 1 is my determinant. So if that number is not in that modular system, make sure you find its congruent number there. And then we need the inverse of 2. Which we've already said is 2. But again, you'd just be looking for what would I multiply 2 by to get a remainder of 1 when I divide by 3. So this is 2. So that's what we're going to use when we normally would say 1 over the determinant of A in our shortcut. We're not going to divide by the determinant of A, we're going to multiply by its inverse. So we'll have 2. And again, that's this 2. Shouldn't have chosen an example that has the same number there. I'm using the 2 that is the inverse of 2, which is 2. Then I take the main diagonal and I just switch those numbers like we normally would, 1 and 2. I switch the sign on the other diagonal, so 0 is going to be 0. This would be a -2 normally. Mod 3, that's a 1. Okay, and if you want to write out that step first, it's a -2, then mod that, that's fine. So then we get 2, 0, 2, 4, which is 2, 0, 2, 1, mod 3. And there's our inverse. Same thing we got with Gauss-Jordan. We already checked it with the Gauss-Jordan one, so we don't really have to check it again. So same process as before. Main difference is you're always modding, meaning you're always going to keep integers in your modular system. And then anywhere you would want to divide, you're actually going to multiply by the inverse. So we would normally have divided by 2 to find the inverse. Here we're going to multiply by the inverse of 2, which is actually 2. Okay, so to encode, we assign numbers to each letter of the alphabet and any other characters you'd want to include. Typically, A is 0, B is 1, C is 2, and so on. There's not a real benefit to scrambling which letters are assigned to which numbers, because the cipher itself will scramble them beyond kind of recognizing any patterns anyways. So typically I would just go in order. If you don't, just make sure whoever is decoding your message has to know the order the letters were in that you decided to assign them to. Okay, then you can choose any square matrix you want as your cipher. Okay, 2 by 2, 3 by 3, 10 by 10, 23 by 23, doesn't matter. Just make sure that the determinant does not share factors with P. So whatever you choose doesn't really matter. You could choose a totally random one as long as the determinant doesn't share factors of P. So if, for example, we do 0 to 25 to assign to the alphabet, your determinant should not be a multiple of 2 or 13. Otherwise, it could be any square that you want it to be. You put your numbers into a corresponding n by m matrix. So like A, our cipher will be n by n, has to be a square. Your message has to share the same number of rows so that I could actually multiply, but it will likely be a rectangle because you'll just load, you'll have A is something like this, and your message will be, going a wide matrix. If you've got a lot of stuff in your message, the number of rows and columns of A have to match rows of M, so you can do the multiplication, but then you just keep on going on the side. You multiply the cipher times the message, mod P, and you'll get gibberish. And then that's the message that gets sent out. The person or machine on the other end gets that gibberish message. They would want to have the cipher, the key, basically, to decode it. They'll find the inverse of that cipher, mod P, multiply the inverse times the encoded message, the gibberish that they got, and they'll get the decoded set of numbers, match them back to letters, and you'll have your original message back. Yeah. So just make sure, again, if your determinant has common factors with P, there is no decoding your message. Your message is lost on the other end. So that's the main reason we want that to occur. Is the whole point would be that something or somebody should be able to decode it to be used, and that can't happen if you share common factors with P. Okay, so multiply cipher times message encodes, multiply inverse of cipher times coded message, and that'll decode. All right, so we're gonna do an example. I'm not gonna do all the arithmetic in between. With a calculator, you should be able to, and again, on your test, expect it to be kind of small, a small message with a 2x2 matrix. Okay, because that makes a lot of the arithmetic less crazy to deal with, is if you have a very short message with a 2x2 matrix, not super difficult to go through the process. 3x3s are already kind of hard to invert. And so if we do that and throw modular arithmetic in there, it's just a lot of arithmetic. But we're going to show, I'm going to show you an example of one, same process in general, so it doesn't really matter. But here we're going to use this cipher to encode the message hello. Okay, and I'm just going to assign A is 0, B is 1, C is 2, D is 3, etc. So my message, H is 7, E is 4, L is 11, so I'll have LL. O is 14, and if I have an odd number and I can't really make it work, you just throw something else in there. Doesn't really matter. You know, I put a 14 again just because I did, so it's hello, but probably what would be smart is if you had punctuation, you'd put that there, or a space, you could put that there, or maybe an uncommon letter that would make a good break in words of like X's or Q's or things where someone would see hello Q, something Q, something X, something X. You'd probably see that as a good break. So you could do basically whatever you want. Just knowing that if I were to string a bunch of words together, if there's no way to kind of see a break there, that might get a little confusing for people. And so then I just do E times M. Okay, E times M gives me 257, 251, 291, 276, 206, 203. Okay, those don't correspond to letters, so it's not the message I'm going to send. This is 23, 17, 5, 16, 24, 21, mod 26. Okay, so I would send the message X, R, F, Q, Y, V. Okay, that's 23, 17, 5, 16, 24. That's sent out to the other person. Okay, there goes the message. Notice, again, what's nice here is like my double L's. There are no double letters in the message. Even the double O's that I added there, they don't show up. So L's don't correspond now to some other number. The pattern is completely scrambled. So there isn't really a decipherable pattern that if someone got that message, they could try and figure out what's happening because they know where double letters are or whatever else happens. It's going to completely scramble it up. Person on the other end then gets that message. They already have the cipher and they have this encoded message 23, 17, 5, 16, 24, 21. They put back in to a matrix. We need the inverse. So we're going to need the determinant of E. So I would just use the cofactors. So like go along, you could use, we looked at elimination to find determinants. We looked at cofactors, whatever. So you do 2 times the determinant of 8, 12, 13, 4, minus 3 times the determinant of 5, 12, 1, 4, plus 15 times the determinant of 5, 8, 1, 13, or whatever other method you want to use, find the determinant. This gives you 583, which is 11 mod 26. Again, with a calculator, sure, you could do that. It's just going to be a lot of arithmetic. Okay, we want the inverse of 11. mod 26, which that is a lot more numbers to check, and also probably a lot less likely that you know the multiples of 26 by heart than you do the multiples of 11, like the example I did. So again, it makes it just a little bit harder to figure out what this is. It's going to be 19, which just means 11, oops, not mod 11, sorry, mod 26. 11 times 19 is 1 more than a multiple of 26. When I do 11 times 19 divided by 26, my remainder is 1. So then the inverse, the decoding matrix, instead of dividing by 11 like we normally would, we're going to multiply by 19, which is the inverse of 11. So we do 19, and then I would do the cofactors, basically. So I go to 2, the cofactors of the determinant of 8, 12, 13, 4. You mod it, and you get 6. Then you would go to 3. The cofactors, you do the determinant of 5, 12, 1, 4. You'd mod it, and you'd get the things. I didn't write them all down. But you'd get your cofactors in there, multiply, and mod it, and that would be your inverse. Okay, that's kind of a lot of arithmetic, but luckily, if you're kind of using this key, once you've got it, you don't have to redo that part again. You'd have the key and you could send information back and forth. Then you'd take the message that you received, multiply from the left side by your inverse. This one I did write down. This one gives you 709, 810, 375, 583, 872, 768. Which is 7, 4, 11, 11, 14, 14, mod 26. So this person would say, oh, hello. Okay, and then you could use that cipher and its key basically to send messages back and forth. You could even use the key as the cipher, send it back, and they already have the decoding key, because if I use E inverse, you have the inverse of that, which was the E that we started with. So you could use that. Probably you'd usually, if you were sending a lot of messages, have a set of keys and have some way to indicate which one you use to do it. So that if someone deciphered one message, they don't necessarily decipher everything, because you might have multiple keys and multiple ciphers that you're using. Okay, we only have a few minutes left, but if you need anything, let me know. Otherwise, you guys have a problem set due tomorrow. I won't see you tomorrow. And then Friday, we have a MATLAB. You guys have a good day today and tomorrow.